Okay, kids, so we're back here uh, talking about something we looked at a little bit in grade 11, reference frames and relative motion. So we'll start with reference frames. So we're in here, we're in section 1.5, and it says, imagine you threw a ball while you were on a train moving at a constant velocity past the station. To you, the ball appears to simply travel up and down under the influence of gravity. So there you are, here you are, you're on the train, you're standing on the train is moving, you throw the ball up, it stops, it comes right back down to the same place. You throw it and catch it out of the same hand. Okay. However, to an observer, okay, stood on the station platform, the ball would appear to move in a parabola. So here's a person here, here's a platform, and they're sitting here watching you throw the ball upward, right? This person here sees this. They see a parabola, right? Where if you were to take the velocity at any point, you were to take the velocity at any point and look at the x component of that velocity, it would be equal. So, however, it says here, to an observer standing on the station platform, the ball would appear to travel in a parabola. There's a parabola with a constant horizontal component of the velocity equal to the velocity of the train. And you can do this in your house. You don't need a train. You can just throw a ball straight up in the air as you're walking and have mom and dad watch you do it as you're. So here's mom and dad, parent guardian. There they are. And here's you. And you're going to walk this way. And while you're walking, you're going to throw a ball up into the air. You're going to see this. Your mom and dad's going to see this. Then switch around. Have mom or dad do it. And you watch them. You're going to see a parabola. I've also included some video links for section 1.5, YouTube videos and such that show this as well. So let's continue here. Let's name these points of view, points of observation. We would call this the train. Oop, let me fix that. We would call this the train reference frame. We would call this the station reference frame. So a reference frame is this point of view where you make an observation. All right, so let's take a deeper look at reference frames. Okay, we're going to take, we're still looking at reference frames. And we're going to put reference frames into two categories. Inertial, it's got the word inert in it. Remember, inert comes from inertia. It's also in there. This is all to do with Newton's first law. So inertia, the inertial reference frames, that's one type of reference frame. And then non-inertial reference frame, that's the other type. Let's deal with inertial reference frames first. So in an inertial reference frame, you're in a situation where there is no acceleration anywhere to be seen or observed from your point of view. So in this type of reference frame, all of Newton's laws are valid. And any frame moving at a constant velocity relative to an inertial reference frame, it itself is also inertial. So let me give you an example here. Here are two frames we're going to talk about. Here are two frames we're going to talk about. So here's a person in a spaceship, and the spaceship is not accelerating. So it's moving forward with a constant velocity. And here's a person in the spaceship, and they're holding a ball. And when they release the ball, because they're out in the middle of nowhere, there's no gravity, they release the ball just stays there. And in another reference frame, let's say uh, there's someone on a space station watching this, they would see that the person releases the ball, and the person and the ball and the whole space station all move forward with a constant velocity, zero acceleration. So the person in the spaceship and the spaceship itself is known as an inertial reference frame. It's moving at a constant velocity. This person here that's just not moving still, it is observing this. It is also in an inertial reference frame. There's no accelerations to be thought of at all in here. That is inertial reference frame. Now, the non-inertial reference frame, very different. In non-inertial reference frame, Newton's first law of inertia does not hold. What? Yep. Why? That's because objects have an acceleration that's not equal to zero. They have an acceleration that's not equal to zero, but even though their acceleration is not equal to zero, all right, there's no net force acting on them. So even Newton's second law is messed up, because basically what we're saying is F net is equal to zero, but acceleration is not equal to zero. What? We need to look at this more deeply. So here we go. Let's do another here. You're in a spaceship. Now here's the spaceship, but now the spaceship is accelerating. It's moving faster and faster and faster and faster. Its velocity is increasing as it moves forward. And here's this astronaut in the space station. They got a little ball here, and they let go of the ball. And they let go of the ball, and the ball rams into the back of the spaceship. But the person in here says, well, this ball is accelerating towards the back of the spaceship, right? But I don't see any force on it. This is breaking the laws of physics, right? So what's happening here is the ball is being released at a certain velocity. Let's call it velocity 1, all right? And it's going to continue moving at velocity 1 because the person's not holding on to it anymore. But the rest of the spaceship has started to increase its speed. So the spaceship is moving faster and faster and faster forward, while the ball is only going to be moving forward at the speed it had, the velocity it had when it was released. So eventually, the back end of this spaceship and the ball are going to have a collision. But the person in here is stuck in this reference frame. That's their point of view. All they're seeing is boom, the ball runs into the back of the spaceship, and I can't come up with a force to explain what is happening here. And now, to a person on a space station watching all this, they can say, oh, I see what's happening here. I see what's happening here. The spaceship's moving on faster and faster and faster. The ball doesn't pick up speed anymore, so it's going to run into each other. This is perfectly in line with the laws of physics. Why? Because this person is still. They're not accelerating. They're not even having a velocity. Here, they can use the laws of physics to explain what's happening here. Here, the person in here is like, I have no idea, because this is my point of view. I don't have a sense of my acceleration, right? All I know is when I release the ball, it flings out the other way. This is a non-inertial reference frame. A ball has acceleration on it, but I can't determine any force acting on it. So a quick recap here about reference frames. Section 1.5, quick recap. Motion is always described with respect to some point of view, a reference frame, a coordinate system with which the motion is described. And we talked about this one, be it with a train or person walking. So example, classroom frame versus Mr. Zafiro walking frame. So picture yourself in a classroom. I'm at the front of the room and I'm throwing a ball up and down. To me, the ball goes straight up and comes straight back down. Why do I think that? It left my hand, it falls back into my hand. Left my hand, falls back into my hand. So picture this x hat, y hat Cartesian plane walking along with me. See how I'm drawing it? The Cartesian plane is part of me. So it leaves at a certain x value, the ball, and it comes back at the same x value as its y value changes. Okay? Now you're in the classroom. Here you are. I'm walking. I throw the ball up and down. You see this because your reference frame has the x hat and y hat coordinate system still not moving with respect to the classroom. So you see the ball moving in a parabola. So this is where we've been at. So what I found here is a neat little animation. It's available online. I'll put the link to it. That tries to show you how things would look as they move depending on your reference frame. And the reference frames are the ground, the person, come on, the river, a boat in the river. What else do we have here? Anything else? No, it looks like this is a barge that moves along at the speed of the river. So let's start this. And then all you do is you hover over something. So if you were a person just sitting on the park bench, this is how you would see everyone's velocity. Just like that. You can even ask it to show you what the velocities are. Oh, that person there is moving at 5, let's say, meters per second. The blue person, the river's moving at 10 meters per second, right? The boat is moving at 30 meters per second. And that black barge here at the bottom, right? It's moving along with the river. So that's from the point of view if you are a person just on a park bench right here watching the world go by. Just sitting here watching the world go by. But that's not the only reference frame you can have while watching all of this motion. There's other reference frames that you can look at, as I said a moment ago. One of the reference frames you can have is, what does this all look like if you're the person walking, the blue person, part of the Blue Man Group? There they are. Come on, there we go. So according to me, I'm still, the ground is moving backwards. Look at the top of the screen here. The ground is moving backwards away from me at -5 meters per second because that's what things look like when you're moving forward. It looks like the background's moving backwards towards you. The river's still moving forward, but not as fast anymore. It's only 5 meters per second. The boat is moving forward 25 meters per second now, not as fast as the person watching it on the park bench. So that's another point of view that you can have. How about the point of view of the water? Oh, look at that. The water looks still. Looks like the sidewalk's moving backwards at -10 meters per second. The boat's moving forward at 20 meters per second. And the barge there at the yellow, it's going along with me, along with the river. So there's that point of view. That point of view. What about if you're on the boat? Oh, now the boat is still and everything's moving backwards. The person -25, the river -20, the sidewalk there -30. So it changes your point of view. All of this. All right. Now the other thing you can do is you can click show ball and a ball is shot off of the barge. And this is what the path of it would look like if you were on the ground watching the ball be thrown straight up and down by someone on the barge. It's our old familiar parabola, right? So from someone, let's say they're right here on the park bench and there's a person on the barge. The barge is this black thing, okay? It looks like it's just going through a parabola, all right? So that also comes up here. Now we're going to do the same thing. We're going to throw the ball from the barge. We're going to throw the ball from the barge, but now uh, we'll take a look at this from the person's point of view. Ready? So we're going to throw the ball. Come on, where's the ball? There we go. And we're going to look at it from the person's point of view. Still kind of parabolic as the person throws the ball up and down, right? Nice parabola. The person throws the ball up and down. So there's that. Now let's take a look at the ball being thrown from the river point of view. Look. See, the barge is moving with the river. So it just goes up and down and up and down. What about from the point of view of someone on the boat? Oh my goodness, it's a parabola as well, but it's in the other direction. See? So this is a neat little simulation that I hope it's helping you understand reference frames and observing velocities from different reference frames. Okay? So let's continue with this. It says the velocity of an object can be described with respect to some reference frame. So what are the reference frames here? There's three reference frames. There's reference frame A, which is a car. I'm going to label A, and here's its reference frame. So you can picture this reference frame moving along with the car stuck to it. Then there's this other reference frame here, right? X hat is east, Y hat is north. And this reference frame is part of this car here. It's stuck to this car here. Car B. This is a sports car. Look at that. Okay, it's aerodynamic. And then the third reference frame is just some dude hanging along the side of the road here, watching what's happening. So we can describe what's happening here from three different points of view. So let's start that. Let's start that. And we looked at this a little bit in grade 11. So look at this. I'm going to read this for you very carefully. The velocity of car A with respect to the ground. So this is what the person that's just hanging out here on the ground is watching. What does this person see? Well, it sees the person moving, or the car moving, car A moving at positive 40 kilometers per hour x hat. Well, how about right here? The velocity of car B with respect to the ground, WRT, with respect to, okay? Well, this person here is watching this car B move at negative 40 kilometers an hour x hat, because it's moving in the negative x hat direction. So now what I'm going to ask you to do is turn that on its head. Turn that on its head. Put yourself in car A right here, right? What does the ground look like it's doing? So the velocity of the ground with respect to someone who's in car A. Well, when you're in a car and you look at the ground, it looks like it's going backwards in the other direction you're moving. So the velocity of the ground with respect to car A would be negative 40 kilometers per hour x hat. Similarly, look here, the velocity of the ground with respect to someone observing the ground while they are in car B. Well, they're going to see the ground move in the other direction. Okay? So if you take a look here, there's a change in direction here. The velocity of the ground as with respect to car B, or the velocity of the ground as observed from the person in car B, is positive, not negative 40 kilometers an hour. Okay? Next one. We want to observe car A as if you're a person in car B. So picture yourself right in here and you're watching the other car. Well, you're going to say, well, that car is coming towards me at positive, because it's moving in the positive x hat direction, 80 kilometers an hour. I'm moving towards it at 40. It's moving towards me at 40 kilometers an hour. 80 kilometers an hour, positive x hat. So this is the velocity of car A as observed by a person in car B. Now similarly, put yourself in car A right here. Let's say you're the driver in car A. What's the velocity of car B as you observe it? Well, you would say the velocity of car B with respect to car A is, well, I'm moving at 40 kilometers an hour. I'm in car A. The other car is moving at me at 40 kilometers an hour, so it's going to move towards me at 80 kilometers an hour. But I see that car B is moving in the negative x-hat direction. So the velocity of car B as observed from car A, or the velocity of car B with respect to car A, is negative 80 kilometers per hour x-hat. So that leads us to forming what we call a general equation. The velocity of any object A with respect to reference frame B is always equal in magnitude, but opposite in direction, there's the negative sign, to the velocity of car B, or object B, any object B, with respect to reference frame A. And if you take a look at here, whenever we switch the letters around, look, the sign changes. Whenever we switch the letters around, the sign changes. Whenever we switch the letters around, the sign changes. And that holds true in any situation. Okay, here's a next example. It's a parade. Remember those parades? They're great. Maybe one day we'll be able to have a parade. Here's a situation. Here's a float. Black platform with wheels. Float. So float is going to be reference frame F. Okay? Now, here is the ball. So here's a person stuck on the float. They're not moving. And they're going to throw a ball forward. So the other reference frame is the ball. And the third reference frame is some person hanging out at the side of the road watching the parade. And this person is standing on the ground. So this will be reference frame ground, G. What's up, reference frame G? Okay? And we're going to establish an x hat, y hat coordinate here that's stuck to the ground, G. And what we want to calculate is the following. What is the velocity of the ball right here? Here's the ball as observed by this person right here on the ground. So the velocity of the ball with respect to the ground. Well, we don't know that explicitly. We're going to have to calculate it. We know that the float is moving with respect to the ground at 10 kilometers per hour x hat. So the velocity of the float with respect to the ground is positive 10 kilometers per hour x hat. That's what the person on the ground is observing. And we do know that the velocity of the ball with respect to the float, so that's what this person, the red person here, is observing. They throw the ball and they observe that the ball is moving at positive 20 kilometers per hour. It's moving in a positive x hat direction. But that's the velocity of the ball with respect to the float. We don't want that. We want the velocity of the ball with respect to the ground. So in order to do that, you're going to have to add the ball's velocity to the float's velocity because the ball was already moving on the float. So how do we write that out? Well, we write it out like this. The velocity of the ball with respect to the ground is equal to the velocity of the ball with respect to the float plus the velocity of the float with respect to the ground. And ball with respect to the float is ball with respect to the float. How much is that right here? Positive 20 kilometers per hour x hat. Float with respect to the ground, what is it? Positive 10 kilometers per hour x hat. And we get an answer of positive 30 kilometers an hour x hat. So the person here watching this sees the ball move at positive 30 kilometers per hour x hat. So that means we can come up with a general equation. The velocity of A with respect to B is always equal to the velocity of A with respect to some other reference frame, let's call that other reference frame X, just for now, plus the velocity of that other reference frame with respect to B. So when you do this, the first letter here has to be the first letter here. Okay? The last letter here, which is B, has to be the last letter here. And then you need some other reference frame, in this case X representing any other reference frame, to link the two reference frames. So this is the general equation for always solving problems like this. And we looked at this a little bit in grade 11. So let's try another example here, two-dimensional example. We did stuff like this in grade 11 with a boat crossing a river. You may remember that. You had a boat crossing a river, but it was a pretty simple question because if you think about it, you know, you had the river and the river had a current, so that would be like velocity of the water with respect to the shore, and it was maybe going in the x-hat direction, and you had a boat that was aimed across the river, so its engines were pushing it across the river, so that was in a y-hat direction, so everything was always 90 degrees, right? And you could figure out what the velocity of the a boat was with respect to the shore because it was 90 degrees. You could use Pythagoras and you could use tan inverse and all that. That was grade 11. No, not so much. We're going to get a little bit more complex, but that's okay. That's okay. You're in grade 12. So here we go. An aeroplane. So that's one of the reference frames, the plane. Has an airspeed. So that's one of the reference frames, the air, of 200 kilometers an hour as it heads due north. So that means the pilot is aiming the airplane due north, just like the boat captain was aiming the boat due north. But a 100 kilometer per hour wind is air, that's the air reference frame, blows from the northeast. So it's blowing from the northeast. Northeast being north 45 degrees east from. That's very important. What is the velocity of the airplane with respect to the ground? That's the next reference frame. So basically what I'm asking is, what's the motion of this airplane look like from someone looking at this from the ground, looking up at the airplane? Are they going to see this airplane go straight north? No. There's a wind that's blowing from the northeast. It's going to push the plane, just like a current would push the boat. But the way to solve it remains the same. The velocity of the plane with respect to the ground is equal to the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. It follows that rule. P is first, P is first. G is last, G is last. And then you need another reference frame, in this case the air, to link the two. Well, we have all of this information. The velocity of the plane with respect to the air, the pilot, he or she, is pointing it north at 200 kilometers an hour. But there's a wind that's coming from the northeast at 100 kilometers an hour. So since it's coming from the northeast, it's actually 45 degrees south of west. If you think about it, here's east, here's north. If it's coming from the northeast, the wind is blowing in a direction which is southwest. So you've got to add these together. Well, you could draw a diagram, you could use sine law, cosine law, geometry, opposite angle theorem, blah, 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 and solve this, but I don't think I want to do that. I want to use components. They're my friend and they're your friends now. That's what we're going to do. All right, let's take a look at this. What have we done here? I've converted this into components. 200 kilometers per hour north. North means it's all positive y hat. There's no x component to it. That's a simple conversion. 45 degrees. I hope you know that at 45 degrees, sine of 45 equals cos of 45. So each component should be the same. So if you sine 45 or cos 45, you get the same number. You multiply it by 100 to find the component. You're going to get a value of negative 70.7 kilometers per hour x hat, right there, negative component, negative 70.7 kilometers per hour y hat. They're both negative. It's going southwest. So now you can collect all your x values. There it is, negative 70.7 kilometers per hour x hat. You can collect all your y values, positive 200 and negative 70.7 gives me positive 129.3 kilometers per hour y hat. And we have calculated, there it is, the velocity of the plane with respect to the ground. Done. Now, if you wanted to, you could take velocity of the plane with respect to ground in component form, and you could convert it back into angle magnitude form. You could do that. Well, what I would do first is I would draw, I've drawn here in yellow, the Cartesian plane x hat east, y hat north. I would draw the components. So here's velocity of plane with respect to ground x hat. That's this part right here, the negative 70.7 kilometers per hour in the negative x hat direction. And then I would draw this one, positive 129.3 kilometers an hour y hat. There it is in green. So I'm going to add the red to the green, vector tip to tail addition, and it gives me the complete vector, velocity of the plane with respect to velocity of the plane with respect to the ground. And I'm going to find this magnitude, and I'm going to find this magnitude by using Pythagoras. Because that's 90 degrees in here. I have a right angle triangle. So I'm going to use Pythagoras. Look, I did it right here, and I get 147 kilometers per hour. Just from Pythagoras. And I want to find this angle right in here. Well, that's no problem. We learned this a while ago. I'm going to use tan inverse. Right? I'm going to use tan inverse. So opposite over adjacent. Opposite green, y component. Adjacent red, x component. I put those magnitudes in here. Notice I'm using magnitudes. Put that in there. Do the calculation. I get 61 degrees. And that 61 degrees is right in here. It's north of west. So my final answer is 147 kilometers per hour, 61 degrees north of west, which is the angle magnitude version of the answer you already calculated in component form. They're both acceptable. They're both right. Okay, have a great day.